Okay. First thing I want to go over with is good maintenance practices on this machine. All right. Make sure whenever you remove a circuit card, you tag it, what's wrong with it. Okay. After it's repaired, make sure you tag it with the repair information on there, so if it doesn't work, you know what's been done to it.
Okay.
The second thing is here, especially here in Saltillo, is you're going to have problems with static electricity.
Okay.
Okay.
Yep.
The components in this machine are extremely sensitive to static. Okay, it's the technology. There is a certain section in there in that machine that's got what we call Meckel devices in it, Motorola emitter controlled logic. Those things, you just look at them wrong and they'll blow. And you can't buy them anymore. There's just no source for those devices anymore. So be extremely, if you look at a print and it says Meckels on it, be extremely cautious. Get wrist straps out, ground yourself, make sure that you do that before you handle these circuit cards. If I get to talking too fast, let me know and I'll slow down. Okay? So just be aware of the static that can the damage that static can cause on this device. And it's just like any other piece of electronics nowadays. To give you an example, I used to work for McDonnell Douglas, and they took those big 200-watt power transistors, you know, the big ones, the TO3 cans and stuff, and they took them and just gave them to people and had them carry them around. And they give them to a person to carry for one day, somebody for a couple of days, somebody for a week or something like that. And then they'd cut them up, cut them open, and they'd go into them and look at them with an electron microscope. After about a week of carrying one of those big, powerful 200-watt transistors around, they were bad because the static electricity had burned through the components inside. So that's how dangerous static electricity can be. We've been kind of careless about how we've been handling them lately and stuff by not grounding ourselves, but you make sure you get some wrist straps so that you ground yourself when you handle these. Enough on that. Like I said before, this is your list of diagrams that you're going to be using the most with this machine. And the ones that out of this list that you'll use the most are the ones starting with S. With S. S01. Okay.
Yes.
These are the system diagrams. And it's all based on location up in the cockpit. Like the captain's instrument panel, the overhead panel, forward overhead panel, the forward overhead aft panel. You know, that's how you're going to try to find this stuff. Once you find it, there's a little bit of a description here. It tells you which prints you're on, but sometimes it's not that helpful, so you got to dig a little bit into the drawings to find it. So that's how you go. So you're going to have, you've got, like I said before, you got several different types of inputs and outputs to this machine. You got discrete inputs, you got discrete outputs, you got DWOs, you got analog inputs and analog outputs. Now, some of these get handled differently. The DWOs is a special case, like I told you, it's used like a more of a row column type thing, where you just want this whole word to handle just a whole bunch of stuff at once. And it's essentially working like a discrete output, but it's a whole word, okay? And it's used as a whole word. The analog outputs get handled in a couple of different ways too. Some of them will come out of the analog output cards that are in the Unit 5 cabinet down there, which is the second cabinet towards us from the back wall. They'll come out, they'll go into the patch panel, they'll go straight up to the cockpit, and they'll drive an indicator.
Yes.
And analog outputs work on a plus and minus 10 volt system. Okay? And basically what it is a DC level that will vary up and down here depending on where you want the indicator to point to. Okay? So minus 10 volts could be the very minimum reading on the indicator, and then plus 10 volts would be the very maximum reading on the indicator. Okay, so it will go minus 10 volts if this is 0, goes all the way up to say 10. That would be plus 10 volts. And then 0 volts will be somewhere in the middle. Okay? So it's not 0 to 10, or is it, it's always between minus and plus is the maximum range that it goes. And depending on the indicator, depends on how far it goes. It might be a full 360-degree turn. It might be only a 180-degree turn. Now, there's a special case for these analog outputs that get used, and it's called a synchro drive, where it takes two analog outputs. Okay, they can be used in a direct DC format, where you got a -10 to +10 volts, and then following 90 degrees behind it is this cosine. So you got sine and cosine. So the sine is going up and down by -10, and then 90 degrees behind it is the other one. Kind of like this is what it looks like. Now, you can find it in a straight DC format depending on what the indicator is built up, how it's built to take it. The other one could be, it goes out like this to an Ezard card, which is an electronic synchro resolver driver. That's what Ezard stands for. Go ahead.
Electronic synchro resolver
driver. Some people call them side drives, which was a side drive is a synchro resolver driver card. They all do the same thing. They just have different names depending on what the manufacturer. Link use Ezard. Okay, so, and what that does is it takes these varying DC levels and turns it into an AC level. Very AC. And that would go between a peak to peak of 26 volts. 26 volts AC.
For some instruments.
Yeah, for some. Some of them work on an Ezard. And then this would be your sine, and then your cosine would be 90 degrees following like this.
Yeah.
Excuse my drawings.
No. We got it.
Okay. So it's a 90-degree shift, and that's what drives the instruments. And the way to tell what's going on with both of these, if you got an instrument that's driving and all of a sudden it just stops, and then it makes a big jump up to here and continues driving, that means that you've lost either the sine or the cosine. It's very easy to detect it, because what will happen is that during this first part here, where this is still at 0, okay, it will drive normally. Then when this is supposed to come up to take this next little bit, okay, it kind of stops, because it's only getting half the signal that it needs, and it will just stop there. And then when they finally match up again here, at this point, it just jumps to that point and then starts driving again. And you'll jump in quarters. Boom, stop, jump, stop, jump, stop. And that's because of the 90-degree shift between the two signals. And you'll find it either with the DC-driven one or the AC-driven one. Okay, so if you see something like that, I've lost either my sine or my cosine on the drive signals for the instrument. So that's how the analogs are done. So you're either going to have a single analog signal driving an instrument, two analog signals driving it in a sine-cosine configuration, or those going over to an Ezard card to convert that two analog signal sine-cosine into an AC level sine-cosine. Okay, so that's how those get used. The other part you got is an analog input. Now there's two types of analog inputs that are used sometimes. Now this machine I can't tell for sure because I've not got enough into it, but it's just the 0, once again it's the plus or minus 10 volts, comes in, hits the interface down there, and it gets converted from an analog signal to a digital word. And it takes a whole word for an analog. So 24 bits of data to create an analog output or an analog input. So it goes through what we call an analog to digital converter, converts it from an analog signal to a digital word format, which the computer takes and calculates the values based on it. And vice versa for the analog out, which you send the digital word out, hits a ladder network, converts it into an analog signal, which then drives your instruments.
Yes, sir.
Okay. Now, you have a special case sometimes which they call an AC input, which is the reverse of an ESR. Takes an AC signal, converts it into a digital analog voltage signal, DC level, and then that will take you back into the through the D to A converters, A to D converters, and convert it back into something that the computer can understand and work with. But I don't know if this machine has any AC input signals. I know some of the other machines I've worked on in the past have had them. Now, the simplest stuff by far is discrete inputs and discrete outputs. Just understand DWOs, discrete word outputs and stuff, work pretty much the same as discrete outputs, but it's a word package format. And what we'll do is we'll kind of look at this one, guys, this print here, and it'll be easier to follow it. And all your input and output, as far as the system diagrams, getting back to the cards, it's going to be very similar, no matter what kind they are. They just go through different circuit cards to get in or get out. Now, the problem that we're having right now up in the simulator is with the external power left bus. It's the AC bus coming from external power. If you turn the switch on and off, it does nothing. And this switch has 28 volts coming off this TV right here. It gets applied to all these switches on here. And it gets applied to the common point on the switch. And then when it's open, or in the off position, this is at a low. Or actually, if you got on there with a voltmeter and look at it, it'd be at minus 5.2 volts. Okay.
Discrete input?
Yeah, on the discrete input. Now, if you close the switch, it takes 28 volts and puts it onto here, and it goes to what we call a logic high. And then the input card will receive that data, and it starts packing all this stuff together. Now, the next step, how do we find where it goes to? And this is going to be similar, the process is similar for everything. So what we got to do is we got to start with the core memory address, which is B266 on this thing. Okay? So you go find B266 in this book. This is where it gets a little hairy. No, not wrong book. This book. Get this? Yep. Now we know this thing is located in 23A21. 23 is unit 3, or sometimes you'll see it just labeled as 3, but it's unit 3. And so you go find unit 3, A21 by looking here. So we're going to look for 3, A21, because they don't put the 2 in this book. So we got to keep going through the pages until we find 21, 3A21. Now you look for this name here in this column right here, the core memory address. Okay, so B226. So we come right down through here looking for B226. Okay, so B226 is between, wait a minute, that's not it. Right there. B222 and B227.
Yes.
It's on octal word 13. It's in the grouping of bits 18 through 23, so it's 6 bits that we're talking about right here, right? Yeah, 6 bits. So B222, B227 is on card that's in slot J110. Okay. Now, okay, how do we go back further from there? Now, this gets a little bit more complicated. So now we go to another book, J110. So, we will use this book. Now you'll find that these books have got all similar data, like that big one over there has got more in it. But so we go to the discrete input system. Let's see if this has got all the pages in it. So now we're looking for J110. Well, this is telling you right here, if we go to J1110, it's got a 503336 card in it. Yeah. Okay. So we find J110. Let's see if this one's got J110. Nah, let's see, it starts at sheet 5. Let's go with this one. This one's complete. Discrete inputs. And then we're going to go to gotta find that.
This book is part of the first.
Oh, no, it's not. I'm getting lost here, guys. This is all the cards.
Missing one book? Maybe the one.
Yeah, which one was I using that had it? Maybe it was the